Okay. The midterm is next Thursday. Next Thursday in the evening. Yeah. If you cannot take the exam at the time, okay, let me know. Let me know.
It will be in this classroom.
Yeah, discussion. And I'm thinking, the topics the exam covers. I think the exam covers the topics today. Law Wednesday. Today, let me see what I am going to talk. Today, first topic, section 6.2, Newton divided difference method to find interpolation polynomial in Newton form. The second topic, section 6.2, 6.3. Termite interpolation. Yeah, I present this topic in the last class, but take a review. Number 3, section 3. Extended Newton divided difference method to solve Hermite interpolation problem. Extended Newton divided difference method. Number 4, section 3. Hermite interpolation polynomial. How good the polynomial approximate function f? I present one result. Interpolation error. Interpolation error. Right, now, topic 1. Right. Given a table of data. There is one and only one polynomial of degree log greater than n. Passes through all the data points. In Newton interpolation form, the polynomial can be written as f x0 f x0 x1 x minus x0 plus f x0 x1 xn times x minus x0 x minus x1 times x minus xn minus 1, not xn, xn minus 1. There is a formula to compute the coefficients. Yeah, this formula. Yeah, f x0 x1 xn is equal to f x0 x1 x2 and xn minus f x0 x1 xn minus 1 and over Based on this formula, we can build a table. The table computes the coefficients of Newton polynomial. The table is yeah. Table. Let's see the table. So let me take n is 4. Okay, n for 4. Build a table. The first column of the table is x0, x1, x2, x3, x4. Second column, divided difference of order 0. x3, x4. Actually, this is the function values. They are function values. Function value at x0, that is y0. Function value at x1. Function value at x2, at x3, at x4. From these two values, by the formula, I can compare divided difference of order 1 at x0, x1. Yeah. From these two function values, I can compare x1, x2 by formula. And from these two, I can compare x2, x3, and x3, x4. Yeah. Because the computations in the third column are independent. Actually, we can compute these values, the entries in the third column at the same time. Right, now, from these two values, they are values, they are numbers. By formula, I can compare f x0, x1, x2. Yeah, formula there. This is the book calls this difference of order 2. Now, from these two, we can compare f x1, x2, x3, and this is f x2, x3, x4. Right. Now, from these two numbers, we can compare x0, x1, x2, x3, and from these two, x1, x2, x3, x4. Finally, from this column, we can compare f x0, x1, x2, x3, x4. Yeah, x4. The coefficients of Newton integration is the first row. First row. This is the coefficient of Newton. Using this table to find Newton integration polynomial is called Newton finite difference method. Let me show you one example. Say, I think I present this example before. Take a look at one example. Say, Here, example. B1. This table. 3, 1, 5, 6. Y is 1, negative 3, 2, 4. Okay. Now I want to find this polynomial. Okay. Now, second column function value. Function values. So let me erase second column function values. Yeah, here just function value. Function values. Yeah. Here. This is 1, negative 3, 2. Oh, n is 3. So I don't need x4. Yeah. x0, x1, x2, x3. So we don't need x4. Yeah, we don't need this x4. We don't need. No, we don't need. Okay. Okay, now let me compare this number. Yeah. The number. Yeah. F x0, x1 by formula, by this formula, it is f x1 minus f x0, then over x1 minus x0. So it is negative 3 minus 1, right? Negative 3 minus 1, then over x1 minus x0. Right? What is x1, x0? This is number 3. 1, 5, 6. So 1 minus 3. One minus 3. What is that? Number 2. So this is number 2. Number 2. Yeah. How about let me use a different color. Now compute this. X1, X2. X1, X2 by formula. X2 minus X1, then over X2 minus X1. Fx2, 2 minus negative 3. So 2 minus negative 3. Then over x2 minus x1. Yeah. So 5 minus 1. This is 5 over 4. Okay, yeah, this number 5 over 4. This is 5 over 4. And similarly, this number is 2. Yeah. 2. This is 2. 2. 2. Yeah. 2. Different color. 2. 2. And this number, negative 3 over 8. Now, let me compare this number as an example. Yeah. Okay, let me compare this. Okay. F x1, x2, x3 by formula F x2, x3 minus F x1, x2, then over 3 minus x1. Yeah. This number is number 2 here. Number 2. So number 2 minus, how about this number? 5/4. 5/4. Then over x3. 6 minus x1. 6 minus 1. Okay. So calculator 3/20. This is a 3/20. So yeah, yes, this number. 3/20. Finally, compute that number. F x0, x1, x2, x4 by formula x1, x2, x3 minus f0, 1, 2, then over x3 minus x0. So it is a 3/20 minus negative 3/8, then over x3 number 6, x0 number 3. So it is 7/40. Yeah. So this number 7/40. Seven over 40. Therefore, Newton interpolation polynomial is this is f x0 is 1. Yeah, 1. Yeah. F x0 x1 number 2. Plus number 2. X minus x0, what is 0? Number 3. Now, plus negative 3/8. Yeah, yeah. Times x minus x0, x minus 3, times x minus x1, x minus 1. Then plus, yeah, this number, 7/40. 7/40 times x minus x0, 3, x minus x1, then x minus x2, 5. Yeah. Then this polynomial passes all the data points. Yeah, this approach to find coefficients is called Newton divided difference method. Yeah, this method can be extended to solve the Hermite problem. Take a review about what is Hermite problem. Okay. Yeah. Okay. This is a topic, second topic. Topic 2. We'll review topic 2. Hermite interpolation. Given some x values, we assume these x values they're different. Yeah. Given some x values. This is x0, x1, x2, xn. We call this x values root. Yeah, root. And also suppose some function values and values of derivatives and the roots are given. Okay. Function value at x0 below. Function value derivative at x0 below. And then derivative k0. What is k0? K0 is some number, some integer. Yeah. -1. Yeah. At x0 below. Yeah. At x1. Function value at x1 below. Derivative at x1 no. And then derivative k1 times k1 -1 times below. Yeah. Pay attention. K0 integer, k1 integer, they can be different. They can be different. At x2, yeah. K2, x2, and this is a f xn, f derivative xn, f kn -1 xn. Now we want to find a polynomial of degree as small as possible. Satisfy these data. Okay. Yeah. How many conditions we want to find? Okay, find a polynomial such that polynomial at xi is equal to function value at xi. Derivative on the polynomial at xi is derivative of the function at xi, and so on. Right. So this is a p. Take derivative ki -1 times at xi is ki -1 at xi, where I between 0 and n. How many equations? I is 0. We have k0, so many equations. I is 1. We have k1. I is n. We have kn. So in total, there are so many equations. The polynomial p, I want the degree as small as possible. The degree should be what? Should be what? Set this number to be m -1. Okay, so I want to find polynomial degree m +1. Okay, m +1, not m -1. Degree m. Okay, so that the conditions are true. Let me give a name. 1. Okay, so that 1 holds. 1 holds. Okay, polynomial of degree 1. It has m +1 coefficients. Yeah. Degree 1. So C0 plus C1 x plus Cn xn. Degree n. How many unknowns? Unknown coefficients? M +1 unknown coefficients. I said m +1 equal to the total number of the conditions. So this polynomial exists and only one. Yeah. because when we solve a linear system, that linear system has m plus 1 unknowns and m plus 1 equations. So this polynomial is one and only one. All right, now the next question is how to determine these polynomials. Okay, how to find p? Okay, how to find p? Let me extend the Newton divided difference method in the previous example to answer this question. Okay. But I need one more formula. Okay, one more formula. The formula. From the last class, properties about divided difference. One property says, okay, yeah, this is from the last class. X0, x1, xn is equal to 1 over n factorial. Suppose the function f has derivatives of order n. So take derivative n times and then evaluate at some point psi. What is psi? Where psi is between the minimum of the root. Yeah. X minimum. That means that minimum x0, x1, xn. And between x minimum and x maximum, what x maximum is? The largest root. Yeah. This is a property that I presented in the last class. In this formula, we assume the roots are different. Now, I let x minimum and I let what? X maximum minus x minimum. Yeah. The distance between the largest and the smallest approach 0. Then we have x0, x1, xn approach the same point. Okay? Approach the same point. Then we have the following formula. Okay. F divided difference at same point. Yeah. This is how many? N plus 1, so many. Is equal to 1 over n factorial. Xn, x0. When the roots are different, we have this formula. When the roots are the same, we define, okay? Define. Right. Define. Right. Divided difference at same points is 1 over n factorial f, take derivative n times at x0. This is a definition, okay? Definition. Yeah, you don't need to ask why, okay? You don't need to ask why. Yeah, I specify that, yeah, finite difference at same points is this, okay? The rationale behind is here. But after we get this, we can consider this as definition. No reason. Okay, just so you know, I use this notation to represent the right side. Now, with this formula, together with the formulas here that I have erased, then I extend the Newton dividing difference method to solve Hermite problem. Okay, take a look at one example. Okay? Yeah. After this example, you know, the extended Newton method. Yeah. This is extended. Yeah. Yeah. This is topic number 3. Extended Newton divided difference method for Hermite problem. What we need are 2 formulas. First formula, okay. First formula, okay. Let me erase. Second formula, only 2 formulas. Yeah. Second formula. X2 xn is equal to f x1 x2 xn minus f x0 x1 xn minus 1. Yeah. And xn minus x0. Yeah. Only these 2 formulas. Yes. Okay. Only these 2. And now let me show you one example. Okay. This is a Hermite interpolation problem. Okay. Example number 2. Given function value. Let me see. Given. Let me make a table. X0 is 1. X2. X1 is 2. Yeah, only 2 points, only 2 rows. Function value at 1 is equal to 2. Derivative at 1 is 3. What else? Function value at 2 is 6. Derivative at 2 is 7. Second derivative at 2 is 8. 5 conditions. Now I want 5 conditions. Degree of polynomial should be 4 because degree 4 polynomial has 5 unknown coefficients. So 5 polynomial in 4 its notation, the set of all polynomials of degree log greater than 4, such that polynomial at 1 is function value. Polynomial derivative at 1 is derivative. Okay. Polynomial at 2 is f2. Polynomial derivative at 2 is f derivative at 2. Polynomial at second derivative at 2 is this. Right. Now I want to determine this polynomial. Now, the solution is okay. Step 1. Introduce new nodes. Now C0 new node, okay, is equal to x0. What is x0? 1. Two conditions associated with x0. Now, second node, C1 is x0 is 1. Okay. Yeah. Because there are two conditions, then I introduce two nodes. Okay. Here, 3 conditions, I introduce 3 nodes. Okay. So C2 is equal to x1. x1 is 2. C2, C3 is x1, 2. C4 is x1, 2. Yeah. 2. Okay. Okay, let me erase again. Here. Then the Hermite interpolation polynomial is okay. What is this? Okay. T F C0. Yeah, actually the Newton interpolation polynomial based on the new root. C0 C1 x minus C0 plus C0 C1 C2 x minus x0 C0 the new root. Okay, C0 C1 and then plus F C0 C1 C2 C3 x minus C0 x minus C1 x minus C2. How many? One more term. F C0 C1 C4 x minus C0 x minus C1 x minus C2 x minus C4 C3. Actually, this is the Newton interpolation polynomial based on the new root. Yeah, this polynomial satisfies all these conditions. Now, first step, introduce new nodes. Now, second steps, compute the coefficients. Compute the coefficients. Okay. I don't have space. How about let me erase. Okay, erase. Now, step 2. Step 2. Compute the coefficients. Here, make a table. Yeah, this is C. 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 C0. What is C0? 1. This is a 1. C1. What is C1? 1. C2. C3. C4. 4. Yes, C4. So this is C2, number 2. Yeah. So this is 2. Yeah. Okay. first column, function value at C0. Yeah, this is a function value at C0. C0, it is a 1, function value at 1. Function value at 1, what is that? I have erased. It is function value number 3. But anyway, okay, now here. C1 is F C1, function value at 1 actually. So this is a F C2. This is a function value at 2. This is a function value at 2. Function value at 2. Yeah, function value. Okay. Now, and then the next column, this is a F C0 C1 next column. So how about let me for have more space? How about let me here? Yeah, here. This is a F1, F1, F2, F2, F2. Yeah. So now I want to compute F C0 C1. Okay. What is that? This is a F C0 is 1. C1 is 1. You agree? Yeah, yeah, right. I have yeah. Okay, now the looks the same, so I use this formula. What is n? N is 1. You agree? This is a 1/1 factorial derivative. N is 1. N is 1. Then n 1. Yeah, it's the formula. So here, let me erase. This is actually this is a F derivative and 1. How about here? This is a C1 C2. Yeah. What is C1 C2? Let me see. C1 is 1, C2 is 2. Yeah. Okay, now looks are different. Then we have two formulas. This is one. Use the second one. This is what? F2 minus F1. Then over 2 minus 1. F2 function value at 2 minus function value at 1. Then over 2 minus 1. Function value at 2. 6. Okay, I have erased. Function value at 1 is 2. Then 2 minus 1. 4. Number 4. Yeah. This is number 4. So now let me erase. Yeah, this is number 4. Okay, now here. This is a F C0, C1. Yeah, C2, C3. Now this is what? C2, number 2, C3, number 2. Same formula. So this is a 1/1 factorial derivative at 2. Yeah. So this is a derivative. This is a derivative at 2. How about here? This is a derivative at 2. Okay, now here, this is a F C0 C1 C2. By formula, this is a F C1 C2 minus F C0 C1. Then over C2 minus C0. C1 C2 is 1, 2 different, but C0 C1 Same, okay, 1, 1, actually, this number, yeah, this number. What is this number? This number is number 3, yeah, actually, this guy is number 3, given to us, number 3. Now, over C0, 2, C2, 2, minus 1. Okay, now, 1, 2, different, so formula, F 1, 2, actually, I have compiled 1, 2. Yeah, actually, number 4. Number 4 minus, yeah, this guy is number 3. Then over 1. So 1. Ah, this number is 1. Number. Yeah. I don't have time, okay, so you can take a look at my notes. So in detail, okay, let me write down. 2, negative 1. This is a 2. This number is 2. 2, 4, 3, 1. And this is a 7, 4. Seven, okay, yeah. This number is 6. This is a 6. And this is a 2. 2, 6, 6, 6. Okay. Now, first column, first row are the coefficients. So therefore, Hermann interpolation is what? Is this, okay? Yeah. Okay. F0, number 2, plus, how about this? Number 3, x minus x0 is 1, plus 1. X minus x0 is 1. X minus 1, plus, how about this? 2. X minus 1, x minus 1, x minus 2. How about this? Negative 1, the minus x minus 1, x minus 1, x minus 2, x minus 2. Yeah, this is a 1, 1, 2, 2. So get now. So therefore, 2 plus 3, x minus 1, plus, okay, x minus 1 squared. This is a 2, x minus 1 squared, x minus 2, minus x minus 1 squared, x minus 2 squared. Now, this is a polynomial satisfied, the given conditions. This approach is called extended Newton divided difference. The key point is introduce new roots and then write down Newton interpolation polynomial corresponding to the new root. Then the polynomial is Hermite interpolation polynomial. Then use table to determine the coefficients. Only 2 formulas. Details is on my notes. You can take a look my notes. I think except the midterm, okay. Today I don't have time to present interpolation error. Yeah, the exam include interpolation error. So half of Wednesday's class. Okay, I will email you about the detail about what will be covered in the exam. Okay.